In this paper, we propose DynamicVLA, a vision language action model for dynamic object manipulation. Current VLA models demonstrate strong generalization in static manipulation, but struggle significantly in dynamic scenarios. At time step 0, the VLA receives an observation and starts inference. However, due to model latency, it only produces the first action chunk after m time steps. Crucially, the first action in this chunk is still conditioned on the observation at time step 0. This introduces a perception, execution gap between when the world is observed and when the action is executed. The action chunk contains n actions, which are executed sequentially. Once these actions are exhausted, the model must again wait m time steps to infer the next action chunk. As a result, VLA control exhibits two compounding issues: interchunk waiting, and repeated perception, execution gaps. This misalignment is harmless in static settings, but in dynamic scenes, inference latency causes actions to lag behind a changing world. To eliminate interchunk waiting, we propose contiguous inference, where the model continues to receive the latest observations and generate new actions while executing previous ones, enabling low latency and timely adaptation to object motion. To bridge the perception, execution gap, we propose latent-aware action streaming, which explicitly accounts for inference delay and discards stale actions, ensuring that only temporally valid predictions are executed. To keep inference latency low, we design a compact 0.4b parameter VLA. We adopt a convolutional vision encoder, FastVIT, to efficiently compress multi-frame visual inputs, and a truncated small LM2360M language backbone to reduce reasoning latency. Actions are generated by a lightweight diffusion-based action expert. To address the lack of datasets for dynamic object manipulation, we propose an automatic data collection pipeline that applies to both simulation and the real world, and scales across multiple robotic embodiments. In simulation, we generate data over 206 objects and 2,800 scenes with randomized dynamics. Using ground truth 6D object poses from Isaac Sim, a state machine controller automatically executes dynamic manipulation. In the real world, human teleoperation fails for fast-moving objects. We therefore treat the real world as a simulator by recovering object states through real-time tracking and 6D pose estimation. This allows us to reuse the same state machine controller for automated data collection. To fairly compare VLA methods in dynamic settings, we introduce the Dynamic Object Manipulation Benchmark. The benchmark evaluates interaction, perception, and generalization in a unified way, revealing that interaction under motion is the primary failure mode of existing VLAs, where DynamicVLA clearly excels. This dimension evaluates closed-loop interaction under evolving object motion. Due to interchunk waiting and the perception, execution gap, existing VLAs are always acting on outdated observations, which leads to failures when object motion changes. DynamicVLA instead keeps actions aligned with the current state, allowing it to adapt reliably to fast and unpredictable motion. This dimension evaluates perceptual grounding under motion. Outdated observations can cause existing VLAs to issue invalid actions, directly triggering a safety reset to the home pose. These failures are not due to poor perception. Existing VLAs still recognize objects accurately but fail due to latency-induced execution misalignment. This dimension evaluates generalization to unseen object and motion patterns. Even under non-uniform and nonlinear object motion, DynamicVLA maintains stable interaction, while existing VLAs degrade significantly. This suggests that latency-aware, closed-loop control generalizes more robustly to unseen and unpredictable dynamics. Thanks for watching. For more information, please visit our project page. Please be careful when doing experiments.